Have you ever stood on a beach in the middle of a moonless night and looked out at that thin black line where the ocean meets the sky? You know the water doesn't just drop off into a bottomless pit, yet your eyes tell you that is the absolute end of the world. Now, take that feeling and multiply it by 1,000,000,000,000. When we look up at the stars, we are asking the exact same thing. Does the universe have a shoreline? Or is it just an endless black ocean that goes on forever? Most people think of space as nothing, just a big empty closet where we keep our planets and stars. But the truth is, space is a physical thing. It is a fabric that can bend, stretch, and maybe even rip. Tonight, we're going on a slow, deep journey to find the edge of existence. We're going to chase light to the beginning of time and see if there is a wall at the end of the universe, or if we are all just walking in a giant cosmic circle. But as we start to peel back the layers of the void, we have to ask a question that might keep you awake. If we actually found a wall at the end of space, what would be sitting on the other side? To truly grasp the answer to where space stops, we first have to strip away everything we think we know about nothing. We have to look at the very ground beneath our feet and the air in front of our faces and realize that we are swimming in something much more complex than a simple void. For centuries, the smartest people on the planet looked at the universe through a very rigid, simple lens. This was the era of Sir Isaac Newton, a man who essentially wrote the rulebook for the physical world as we know it. Newton was a genius, but his view of the universe was very mechanical. To him, space was an absolute. He thought of it like a giant, eternal, empty theater. The stage was already there. It was fixed, unchanging, and infinite in every direction. In Newton's mind, if you took away all the stars, the planets, and the people, the theater would still remain. It was a passive container. It didn't react to what was happening inside it. It didn't move, it didn't stretch, and it certainly didn't care about time. In this Newtonian world, space was just the where of existence. It was the empty box that held all the stuff of the universe. It was tidy, it was logical, and for a few hundred years, it seemed like the absolute truth. But then, at the turn of the 20th century, a young man working in a patent office in Switzerland started asking questions that felt like they belonged in a dream. This was Albert Einstein. He wasn't looking through a telescope, he was looking through his own mind. He started to wonder, what would happen if I could catch up to a beam of light? What would happen if I were on a train moving at incredible speeds? These daydreams led him to a realization that shattered Newton's theater into 1,000,000 pieces. Einstein realized that space and time are not two separate things. They are tied together, like the threads in a piece of fabric. He called this four-dimensional construct spacetime. And more importantly, he realized that this fabric is not passive. It isn't just a nothing that sits there while planets move around. Spacetime is a physical, dynamic entity. It reacts to mass and energy. It bends, it warps, it twists. I remember the first time I really tried to wrap my head around this. I was sitting on a park bench on a very still, humid afternoon. There wasn't a breath of wind. I watched a single leaf detach from a branch and drift slowly down to the grass. Normally, we'd say the leaf fell because of gravity, and we'd think of gravity as a force pulling it down. But I tried to look at it through Einstein's eyes. I tried to imagine that the air wasn't just gas, but a literal invisible trampoline fabric that the leaf was sliding through. Think about that trampoline for a second. If you have a massive bowling ball and you place it in the center of a trampoline, the fabric curves and dips around it. If you then take a small marble and roll it across the trampoline, the marble doesn't move in a straight line. It follows the curve of the fabric. It falls toward the bowling ball. But the bowling ball isn't reaching out and grabbing the marble. The marble is simply following the path that the ground has laid out for it. This is what gravity is. The Earth isn't pulling on you with a magical invisible rope. The Earth is so heavy that it has warped the very fabric of space around it. You aren't being pulled down, you are simply resting in the dip that the Earth has made in spacetime. When we talk about where space stops, we're talking about the end of this fabric. If space is a material that can be bent and warped, then it has a structure, it has a thread count. Now, let's go deeper into the void. Imagine we leave the Earth. We fly past the moon, past the glowing gas giants, past the icy rocks at the edge of our solar system, and we head out into the empty space between stars. In our minds, we think of this as a place of total silence and total nothingness. But science has shown us that empty space is anything but empty. In the mid-20th century, physicists began to realize that the vacuum of space is actually a seething ocean of activity. This is the world of quantum field theory. Imagine a calm pond. From a distance, the surface looks like a perfect, smooth sheet of glass. It looks like nothing is happening. But if you zoom in, past the surface, down to the molecular level, you see that the water is a chaotic mess of molecules bumping into each other, vibrating and moving at high speeds. Space is the same way. At the Planck scale, the smallest level of reality imaginable, space is a quantum foam. Tiny particles, often called virtual particles, are constantly popping into existence out of the vacuum and then winking out of existence a fraction of a second later. They appear in pairs, dance for a moment, and then annihilate each other. This isn't a theory. We have actually measured the effects of this in labs. It's called the Casimir effect. This tells us that space has a thickness. It has a background energy that never goes away. Even if you cooled a room down to absolute zero and removed every single atom, the space inside that room would still be humming with this vacuum energy. This is a humbling thought. You can never truly be in a place of nothing. Here's an unexpected story that brings this home. In the 1940s, a Dutch physicist named Hendrik Casimir predicted something bizarre. He said that if you took two perfectly smooth metal plates and put them incredibly close together in a complete vacuum, they would be pushed toward each other by nothing. Scientists thought he was insane. How could empty space push on something? But when the experiment was finally done decades later, the plates moved. The nothingness between them had fewer virtual particles than the nothingness outside them, creating an imbalance. The vacuum itself was exerting pressure. We had measured the weight of nothing. I once heard a story about a scientist who was obsessed with the idea of a perfect vacuum. He spent his entire career building more and more advanced chambers, using more and more powerful pumps to suck out every last stray atom of hydrogen. He wanted to see what the universe looked like when the actors were gone. He wanted to see the raw, naked face of the theater. But what he found was that the more he emptied the chamber, the more he realized that the chamber itself, the space inside it, had a geometry. It had a weight. It had the ability to transmit light and bend under gravity. He realized that nothing is a physical thing. So, if space is a physical fabric, like a piece of invisible spandex stretching across the billions of light years of the cosmos, we have to ask the ultimate question: does that fabric eventually run out? If you were in a spaceship that could travel at 99% the speed of light and headed out in one direction for 1 trillion years, would you eventually reach a spot where there is no more foam? Would you reach a place where particles no longer pop in and out of existence? Imagine reaching the very last thread of the cosmic spandex. If you reached out your hand and tried to push it past that edge, what would happen? Would your hand move through into some other place that isn't space? Or would you hit a barrier made of something we don't have a name for yet? This is what we call an information gap. In science, an information gap is a place where our current math and our current observations simply stop working. We can describe the inside of the theater perfectly, but our equations don't know how to handle the outside. The idea of a wall at the end of space feels intuitive to us because everything in our lives has a wall. Your house has walls, your city has limits, the earth has a crust. But the universe doesn't have to follow those rules. Some people think that if you tried to reach the edge, you might find that space becomes so warped and so curved that you'd simply find yourself turned around without ever knowing it. I think about this sometimes when I am staring at the ceiling at 2 a.m. We are so used to the idea that things have an end. But what if space is finite but unbounded? It's a fancy term, but think of it like an old-fashioned video game screen. If your character walks off the right side of the screen, they immediately reappear on the left side. There is a limited amount of level to play in, but there is no wall that stops you from moving. You can walk forever, but you are just looping through the same area. Could the universe be a giant 3D version of that game screen? If we fly far enough, do we eventually just come back to where we started? And if we do, what is that loop sitting inside of? Does the theater have an exterior, or is the theater all that ever was and all that ever will be? As we move forward, we are going to look at the bubble we live in, the observable universe, and see how it creates a fake edge that tricks our eyes every night. But before we get there, I want you to sit with this idea. The very air in front of you, the gap between your fingers, is a living, humming fabric that connects you to the most distant stars. You are never truly in a void. You are always on the stage. But here's what keeps me up at night. If the stage is stretching, as Edwin Hubble discovered, does that mean the theater is getting bigger? And if the theater is getting bigger, what is it growing into? Is there a room that contains the theater? Or is the idea of a room just another illusion our limited minds created because we can't grasp what it means for something to expand without an outside? Because light takes time to travel, we live inside a bubble called the Observable Universe. This is not just a convenient phrase used by astronomers, it is a hard physical limit on our reality. It is the ultimate no trespassing sign written into the laws of physics. To understand why we can't see the end of space, we have to understand the peculiar, stubborn nature of light itself. In our everyday lives, light feels instantaneous. You flip a switch and the room is bright. You look at your hand and you see it exactly as it is right now. But that is an illusion born of our tiny human scale. Light travels at about 300,000 kilometers per second. That sounds fast, and it is, but the universe is unimaginably, depressingly vast. Think of it like a cosmic mail system. If a light bulb is turned on a mile away, it takes a tiny fraction of a second for that mail to reach your eyes. On the scale of a city, that delay is invisible. On the scale of a planet, it starts to matter. When we look at the moon, we are seeing it as it was 1.3 seconds ago. When we look at the sun, we are seeing a version of it from 8 minutes ago. If the sun were to suddenly blink out of existence right now, we would continue to sit in its warmth, blissfully unaware, for 8 whole minutes. We are always living in the past. Now, stretch that delay across the grand expanse of the cosmos. When we point our most powerful tools, like the James Webb Space Telescope, toward the deepest reaches of the void, we aren't just looking at things that are far away. We are literally looking into the past. We are seeing galaxies as they were 13 billion years ago. We are seeing the universe in its infancy, long before the Earth was even a swirl of dust in a primitive solar system. It is a cosmic time machine, but it comes with a built-in expiration date. Since the universe began roughly 13.8 billion years ago, we can only see light that has had enough time to reach us in that window. This creates a sphere around us. If a galaxy is so far away that its light would take 15 billion years to reach us, we simply cannot see it. It doesn't matter how big our telescopes are or how long we stare. The mail simply hasn't arrived yet. Imagine you are standing in a dense forest in the middle of a very thick gray fog. You can see about 20 feet in every direction. Within that 20-foot circle, you can see every leaf, every twig, and every beetle crawling on the bark. But beyond that 20 feet, everything is a blur of white. There could be a massive mountain just 30 feet away. There could be a bustling city, a deep canyon, or the very edge of the world, but you would never know it because the light cannot get through the fog to reach your eyes. Our observable universe is that 20-foot circle. It is a boundary of information, not necessarily a boundary of space. But here's the unexpected twist that usually breaks people's brains. The universe is not a static forest, it is expanding. While the light from those distant ancient galaxies was traveling towards us, the space it was traveling through was stretching out like taffy. It's like trying to run toward a friend on a treadmill that is getting longer every second. Even though the light has only been traveling for 13.8 billion years, the galaxy that sent that light is now much, much farther away than it was when it started its journey. Because of this stretching, the edge of the part we can see isn't 13.8 billion light-years away. It's actually about 46 billion light-years away in every direction. This means we are trapped in a sphere of light roughly 93 billion light-years across. This is our cosmic bubble, our local neighborhood in the grand scheme of things. But just because we can't see past that 46 billion light-year mark doesn't mean there is nothing there. It's like standing on the deck of a ship in the middle of the Atlantic Ocean. You can see the horizon line all around you, 360 degrees of blue water meeting blue sky. You know with absolute certainty that the ocean keeps going past that line. You know there are other continents, other islands, and thousands of miles of water you can't see. You just need to keep sailing to find them. But what if we could never keep sailing? In our universe, the ocean is expanding so fast that we can never reach the horizon. In fact, the horizon is actually moving away from us. I want to share a moment of personal insight here. Sometimes I find this reality deeply lonely. We talk about the observable universe as if it's this grand achievement of science, but in another light, it's a cage. It means there is a finite limit to what we can ever know. There are trillions of stars and potentially millions of civilizations that might exist just 1 inch past our line of sight. They are having their own histories, their own wars, their own discoveries, and we will never ever see them. They are essentially in a different universe as far as we're concerned, because no information can ever bridge the gap between us. This brings us to a concept called the cosmic event horizon. Think of this as the ultimate point of no return. Because the expansion of space is accelerating, galaxies that are currently at the edge of our bubble are moving away from us faster and faster. Eventually, they will be receding so quickly that the light they emit today will never reach us. Not in a billion years, not in a trillion years. They're falling over the edge of our horizon. Imagine you are watching a friend walk away from you on a long street road. Usually, they just get smaller and smaller until they disappear. But in our universe, the road is stretching. Your friend is walking away, but the ground beneath their feet is also pushing them away. Eventually, they cross a line where the road is growing faster than they can walk back. They wave goodbye, and you see that wave, but any wave they make after that line will never reach your eyes. They have vanished into the unobservable void. We are currently losing galaxies. Every year, more and more distant stars slip over this edge. We are living in the golden age of astronomy because right now, the sky is full of light. But if we wait long enough, trillions of years, the expansion will have pushed every other galaxy so far away that an astronomer living on Earth, if it still exists, would look up and see nothing. They would see our own Milky Way and then a total infinite blackness. They would think they were the only galaxy in existence. They would have no way of knowing that the universe was once full of 2 trillion other galaxies. Their bubble would have shrunk to a single island in a dark sea. Here's an unexpected story that illustrates just how strange this cosmic isolation is. In 2007, a team of astronomers discovered something bizarre in the constellation Eridans. They called it the Cosmic Void, a region of space nearly 1 billion light-years across that contains almost no galaxies. At first, they thought it was an error in their data. Voids exist, but not this big. When they confirmed it was real, they realized they were looking at the future. In trillions of years, this is what the entire visible universe will look like to our descendants. Vast emptiness with tiny islands of light scattered so far apart they might as well not exist. We are currently looking at tomorrow's loneliness. Does that make our bubble a lie? Is the edge of the observable universe just a trick played on us by the speed of light? If we could somehow teleport, instantly, breaking the laws of Einstein, to the very edge of our 93 billion light-year bubble, what would we see? Would we see a universe that looks just like ours, with the same patterns of stars and the same hum of background energy? Or would we find ourselves staring into a literal nothingness? One of the most haunting ideas in physics is that the universe might be much, much larger than our bubble, perhaps 10 to the 231 times larger. If that's true, our 93 billion light-year sphere is just a single drop of water in a vast, global ocean. But if the ocean is that big, does it eventually hit a shore? If we could travel past the fog of our perception, would we find a brick wall, or would we find that the universe just keeps going and going and going until the very concept of going loses all meaning? We often assume that because we are the ones doing the observing, we must be at the center. It's a very human ego trip. We look at our bubble and see ourselves in the middle, but every single point in the universe is the center of its own observable bubble. If there is an alien on a planet 40 billion light-years away, they see a bubble that overlaps with ours and includes things we can't see and excludes us from their past view. This creates a beautiful, overlapping web of reality, but it still doesn't tell us where the whole thing stops. It only tells us where our vision stops. We are like people living in a house with no windows, trying to guess the shape of the city by looking at the wallpaper. But what if the expansion itself is the key? If the dough of space is rising, as Edwin Hubble discovered, then it must be rising into something, right? Or is the outside just another illusion our brains created because we can't handle the idea of true infinity? And here's the question that haunts me most. If we are trapped in a bubble that's shrinking, losing galaxies every day to the accelerating expansion, are we watching the universe die? Or are we watching it give birth to something new in regions we can never see? One of the most transformative discoveries in the history of human thought happened on a quiet mountaintop in California in the late 1920s. A man named Edwin Hubble was peering through the world's largest telescope at the time, the 100-inch Hooker telescope at Mount Wilson. Before Hubble, most scientists, including Albert Einstein, assumed that the universe was static. They thought it was a fixed, eternal thing that just existed. It was a comfortable idea. It meant the universe had always been here and always would be. But Hubble noticed something that made his heart skip a beat. When he looked at distant galaxies, he saw that their light was shifted toward the red end of the spectrum. In physics, this is called a red shift. It works just like the sound of an ambulance siren. When the ambulance is racing toward you, the sound waves are squashed together, and the pitch sounds high. As it passes you and speeds away, the sound waves are stretched out, and the pitch drops to a low drone. This is the Doppler effect. Hubble realized that light does the exact same thing. If a galaxy were moving toward us, its light waves would be squashed, making them look blue. But almost every galaxy Hubble looked at was red. They were all screaming away from us at incredible speeds. But here was the real kicker. The farther away a galaxy was, the faster it was receding. This wasn't just a few random stars moving around. This was a universal pattern. It was the first evidence that the universe is not a static room, but an expanding balloon. This discovery led to what we now call the raisin bread analogy, which is probably the most helpful and descriptive way to visualize the expansion of space. I want you to really picture this in your mind. Imagine you are a baker, and you've just mixed a giant batch of dough. Inside that dough, you've scattered hundreds of raisins. The raisins represent galaxies, and the dough represents the fabric of space itself. You knead the dough, shape it into a loaf, and slide it into a warm oven. As the dough begins to bake, it starts to rise. It expands in every direction at once. Now, if you were a tiny microscopic creature living on one of those raisins, you would look out and see all the other raisins moving away from you. The raisin an inch away might move an inch further. The raisin on the far side of the loaf would seem to be racing away at a much higher speed. But, and this is the crucial part, the raisins are not swimming through the dough. They aren't using little raisin arms to push themselves along. They are just sitting there, perfectly still. It is the dough between them that is stretching and growing. In our universe, space is the dough. Every single second, there is literally more space being created in the gaps between galaxies. This expansion is happening everywhere. There is no central point. There is no middle raisin that started it all. If you moved to a different raisin on the other side of the loaf, the view would be exactly the same. Every other raisin would still look like it was moving away from you. I think about this metaphor sometimes when I'm standing in a crowded subway or a busy city street. We feel so cramped, we feel like we are running out of room. But on a cosmic scale, the universe is doing the exact opposite. It is constantly making more room. It is a terrifyingly beautiful thought. The very vacuum of space is giving birth to more vacuum every moment of every day. We are living on a speck of dust in a loaf of bread that is growing into a void that might not even exist. But this brings us back to our big question. What is the dough expanding into? In our everyday lives, if something gets bigger, it needs a place to go. If you blow up a balloon, it takes up more volume in your living room. If you grow a plant, it takes up more space in the garden. Our brains are hardwired to think in terms of containers. We assume that for the universe to get bigger, there must be some extra room outside of it for it to move into. We imagine the universe as a bubble sitting in a giant, dark, empty warehouse. But according to the math of general relativity, the universe doesn't have a warehouse. It doesn't have an outside. This is the part that makes my head spin every time I try to think about it. Space is not expanding into anything, it is simply the internal distances that are getting larger. If the universe is infinite, then there is no edge for it to move past. It is already everywhere. It just becomes more everywhere. If it is finite, it might be curved in a way that it is its own container.
For a long time, scientists thought they understood the oven that was baking this bread. They thought that the expansion started with the Big Bang and that gravity, the cosmic glue, would eventually slow it down. They thought that because all the galaxies have mass, they would pull on each other like a bunch of rubber bands. Eventually, the expansion would stop and the loaf would collapse back in on itself in a big crunch. But in 1998, we got a shock that changed physics forever. Two independent teams of astronomers were studying distant exploding stars called Type 1a supernovae. They expected to see the expansion slowing down. Instead, they found that it was speeding up. The bread isn't just rising, it's exploding outward. This acceleration is caused by something we now call dark energy. We have no idea what it actually is. We can't see it, we can't smell it, and we can't catch it in a lab. But we know it's there because we can see what it's doing to the galaxies. It acts like a kind of anti-gravity that is built into the very fabric of space. As space expands, there is more space. And because dark energy is a property of space, there is more dark energy. This creates a runaway effect. The more space we have, the faster it pushes itself apart. Here's an unexpected story that captures the shock of this discovery. When Saul Perlmutter, one of the leaders of the supernova study, first saw the data showing acceleration, he thought his team had made a catastrophic error. They spent months checking and rechecking everything, their telescopes, their equations, even the basic assumptions of physics. At one point, Perlmutter said he felt like he'd walked into his kitchen and found water flowing upward out of the sink. The discovery was so contrary to expectation that both teams independently delayed publishing their results for months, convinced they must be wrong. But they weren't. The universe really is tearing itself apart, and we have no idea why. I want to be vulnerable with you for a moment. This discovery actually scares me more than almost anything else in science. It points toward a very lonely future. If dark energy keeps pushing the galaxies apart faster and faster, they will eventually be moving away from us faster than the speed of light. One by one, the galaxies we see in the night sky will slip over the event horizon of our vision. They will vanish. Imagine a child holding a handful of balloons in a park. One by one, the strings slip through her fingers. At first, she can still see them, bobbing just above her head. But then they drift higher and higher until they are just tiny dots, and finally they disappear into the blue. That is what the future of our universe looks like. Eventually, every galaxy outside of our own local group will be gone. An astronomer living on Earth in the distant future will look up and see a completely empty sky. They will have no way of knowing that trillions of stars ever existed. They will think they are alone in a dark, infinite room. But does this expansion have a limit? If you stretch a piece of dough too far, it eventually develops holes. It thins out until it snaps. Can space snap? There's a theory called the Big Rip. It suggests that if dark energy gets stronger over time, it won't just push galaxies apart. It will start to pull apart the galaxies themselves. Then it will pull apart solar systems, then planets, and eventually it will become so strong that it will overcome the forces holding atoms together. Everything in existence, every star, every mountain, every person would be shredded into nothingness by the very space they occupy. It would be the ultimate end of the story. But we aren't there yet. Right now, the dough is still rising and the raisins are still visible. We are in a unique window of time where we can actually see the bread and wonder about the oven. But the question of where space stops is tied to how it expands. If space is being created every second, then the edge is always moving. It's a finish line that is running away from us at millions of miles per hour. This creates a loop of curiosity. If space is constantly being created, where is it coming from? Is it being pumped into our universe from another dimension? Or is it a fundamental part of the pixels of reality we talked about earlier? And here's what I can't stop thinking about. If dark energy is a property of space itself, and more space means more dark energy, are we living inside a cosmic feedback loop that will eventually consume everything? Or is there a threshold, some critical density of space, where the expansion suddenly stops or reverses? Could the universe have a natural break built into its fabric that we just haven't discovered yet? And if we did find that break, would we dare to touch it?
If we want to know where space stops, we have to know what shape it is. This might sound like a weird question. After all, when you look around your room, space just looks like, well, space. It's up, down, left, and right. It feels like a box. But on a cosmic scale, the fabric of the universe can have a global shape that defines everything about our future. In cosmology, there are essentially three blueprints for the universe: flat, closed, or open. Think of a flat universe like a giant, infinite sheet of paper. This is the simplest version of reality. In a flat universe, the rules of geometry that you learned in school stay true no matter how far you travel. If you draw two parallel lines on a flat sheet of paper and extend them for 1,000,000,000,000 miles, they will never, ever meet. If you draw a triangle, the angles will always add up to exactly 180 degrees. This version of the universe is infinite. It has no edge, no end, and no boundary. It just goes on, a never-ending plane of stars and galaxies. Now, compare that to a closed universe. This is where things get interesting. Imagine the surface of a globe, the Earth. The surface of the Earth is finite. There is only a certain amount of ground to walk on, but, and this is the key, it has no edge. You can walk in a straight line forever and you will never hit a wall. You will never find a spot where you fall off the world. Instead, you would eventually just find yourself back where you started. You've walked in a circle without ever turning your feet. If the universe is closed, it means that space is curved back on itself.
It would be a three-dimensional version of that globe's surface. In this version, space is finite. There is only a specific amount of universe. But because it loops, you could never reach the end. If you pointed a powerful enough laser into the sky and waited billions or trillions of years, the light would eventually travel all the way around the curve of the cosmos and hit you in the back of the head. The third option is an open universe, which is shaped like a giant saddle or a Pringle chip. It curves outward. In an open universe, parallel lines actually drift away from each other over time. If you and a friend started walking perfectly parallel to each other, you'd find that after a few million miles, you were miles apart, even though neither of you turned. Like the flat universe, an open universe is infinite. It just stretches out in a way that makes everything feel like it's flying away into a never-ending bowl. The weirdest thing about all of this is that we cannot tell for sure which one is true just by looking out the window. It's like being a microscopic ant on the surface of a giant balloon. To that tiny ant, the ground looks perfectly flat. It looks like a never-ending sheet of rubber. The ant has no idea it is actually living on a curve because it is too small to see the big picture. It can't see the horizon where the balloon starts to bend. We are that ant. Our observable bubble is 93 billion light-years across, which sounds huge, but in the grand scheme of a potentially infinite universe, it might be smaller than a grain of sand on a beach. To find out the true shape of space, we have to look for the curve. Astronomers have actually tried to measure this by looking at the cosmic microwave background, the ancient light left over from the Big Bang. They look for the density of the universe. If there is enough matter and energy in the universe, their combined gravity will pull space inward, creating a closed loop. If there isn't enough, space will fly open like a saddle. And if the amount is just right, what scientists call the critical density, the universe will be perfectly flat. I want to share a moment of personal insight here. I remember being in a planetarium when I was younger and hearing the presenter say that the universe appears to be flat within a 1% margin of error. It actually bothered me. It felt too perfect. Why would the universe be exactly at that tipping point? It's like balancing a pencil on its tip and having it stay there for 13 billion years. If the universe were even a tiny bit more dense, we'd be in a loop. If it were a tiny bit less dense, we'd be flying apart. It feels like we're living on a knife's edge. But let's play with the closed idea for a second, because it's the most haunting one. If space is a loop, that means the universe is finite. There is a crust to the bread, even if we can't reach it. It means there is only a certain amount of room in existence. Does that make the universe feel smaller to you? In a flat, infinite universe, the possibilities are endless. But in a closed universe, we're essentially trapped in a giant cosmic hall of mirrors. There was a fascinating study where astronomers looked for what they called circles in the sky. They were searching for patterns in the heat maps of the universe that would prove we live in a loop. They were looking for the cosmic version of seeing your own reflection in a house of mirrors, looking for a specific cluster of galaxies in one direction and then finding that same cluster in the exact opposite direction. They didn't find them. But that doesn't necessarily mean the curve isn't there. It just means the balloon we live in is so mind-bogglingly massive that our 93 billion light-year bubble isn't big enough to notice the bend. It's like trying to see the curve of the Earth by looking at a puddle in your driveway. You're just not zoomed out far enough. Here's an unexpected story that captures how hard it is to measure the shape of the universe. In 2003, a physicist named Jean-Pierre Luminet proposed that we might live in a dodecahedral universe, a 12-sided cosmic soccer ball. He and his team analyzed the cosmic microwave background and found patterns that could match this shape. In this model, if you traveled far enough in one direction, you'd see the back of your own head, but reflected through the strange geometry of a 12-sided mirror. The universe would be like an Escher painting made real. While most physicists now doubt this specific model, the fact that we seriously considered it shows how little we actually know about the shape of reality. I think about the implications of a closed universe when I'm feeling restless, the idea that no matter how far we run, we are just coming home. It turns the entire cosmos into a self-contained system, but it raises a question that science struggles to answer. If the universe is a loop, What is the loop sitting inside of? Does the circle of space exist in a larger void? Most physicists will tell you that the question itself is flawed. They say that space is the only thing that exists and it creates its own geometry. There is no outside. But as humans, we struggle with that. We want there to be a beyond. We want to know what's on the other side of the curve. This brings us to a terrifying thought, the trapped universe. If space is a loop and it is expanding, it means the loop is getting bigger. But if dark energy eventually rips the fabric of space apart, the loop breaks. What happens to a circle when you cut it? It becomes a line with two ends. Does that mean the universe would suddenly develop edges where there were none before? We are currently living in a window of time where the geometry of the universe seems flat to our eyes. But as our technology gets better, we're looking for the tiniest microscopic bump in the fabric that might tell us we're actually on a curve. If we find that bump, everything we know about infinity goes out the window. We would have to accept that we live in a finite room with no doors. But if we don't find the curve, if the universe is truly perfectly flat, then we're faced with the opposite problem, the nightmare of infinity. In a flat universe, space never ever stops. It just keeps going until time itself loses meaning. This creates a new loop of curiosity. If space is a flat, infinite sheet, does it have the same pattern everywhere? Or if you traveled far enough, would you reach a frontier where the stars look different, or where the atoms themselves are put together in a way that our science can't explain? Could there be regions of the infinite universe where the laws of physics are different, where electrons orbit in reverse, or where time flows backward? And if such regions exist, would crossing the boundary between them feel like hitting a wall, even though technically there's no wall there?
If our measurements are right, and the universe is truly perfectly flat, then we have to confront the most overwhelming concept in the history of human thought: infinity. In our daily lives, we use the word infinite to describe a long line at the grocery store or a boring meeting. But true physical infinity is a monster that destroys our sense of being special. If space is flat and it never, ever stops, then we are living in a room with no walls, no ceiling, and no floor, just an endless expanse of more. Infinity isn't just a very large number. It is a completely different kind of reality. To understand what an infinite universe really means, we have to look at how matter is arranged. Think of the universe as a giant bucket of Lego bricks. There are only so many ways you can snap those bricks together. You can build a house, a car, or a tree, but eventually, if you have a big enough pile of bricks and you keep building forever, you are going to run out of new designs. You will eventually have to build the exact same house twice. The universe works the same way. Every single thing you see, the screen you're looking at, the chair you're sitting in, the very DNA inside your cells is just a specific arrangement of atoms. In a finite bubble, those arrangements are unique, but in an infinite universe, the number of possible ways to arrange atoms is finite, while the amount of space is infinite. This leads us to the Doppelgänger Paradox, and it is one of the most unsettling conclusions in modern cosmology. If you travel far enough in a flat, infinite universe, the laws of probability dictate that you must eventually run into another version of yourself. I'm not talking about someone who looks like you or has the same name. I am talking about an exact, atom-for-atom duplicate. Somewhere out there, trillions of light years beyond our cosmic horizon, there is another planet Earth. It has the same oceans, the same history, and the same people. And on that Earth, there is another you. That version of you is wearing the same clothes, has the same memories, and is currently listening to a voice tell them about the paradox of infinity. I want to pause here and be honest about how this feels. It's a moment of personal vulnerability for many scientists. We like to think of ourselves as individuals. We think our lives are a one-time only event in the history of the cosmos, but infinity takes that away. It turns us into a repeating pattern. It suggests that there isn't just one of you, there are an infinite number of yous. Some are doing exactly what you're doing.
Some made a slightly different choice this morning and are having a better day. Some made a choice that changed their entire life. I once spent an entire night walking through a quiet neighborhood, looking at the glowing windows of the houses and trying to visualize this. I tried to imagine a line stretching out from my chest, going past the clouds, past the moon, through the center of the galaxy and out into the void, for a distance so large the number doesn't have a name. And at the end of that line, there was me, looking back. It makes the edge of space feel like a mercy. If space had a wall, we could be unique. Without a wall, we are just a line of code being copied and pasted forever. But let's look at the unexpected story of the infinite monkey theorem. You've probably heard the idea that if you give a monkey a typewriter and an infinite amount of time, it will eventually type out the complete works of William Shakespeare. It sounds like a joke, but in an infinite universe, it is a physical law. Not only would the monkey type Shakespeare, but it would type every book ever written, every secret you've ever kept, and the exact time and date of your own death. In 2003, a group of researchers at the University of Plymouth actually tested this theory. They put a computer keyboard in an enclosure with 6 Celebes-crested macaques. After a month, the monkeys had produced 5 pages of text, mostly the letter S. They also destroyed the keyboard by urinating on it and hitting it with rocks. While this experiment was tongue-in-cheek, it illustrates a profound point. Even in infinity, some things are so improbable that they might as well be impossible. But in a truly infinite universe, even the improbable becomes inevitable. Those monkeys would eventually type Shakespeare, you just have to wait longer than the current age of the universe. Infinity has all the time in the world. In an infinite space, everything that can happen must happen, and it must happen an infinite number of times. This changes the way we think about the end of space. In an infinite universe, there is no end. You could fly in a straight line for 100 trillion years and you would never hit a barrier. You would just keep passing more stars, more galaxies, and eventually more versions of yourself. The edge becomes a psychological boundary, not a physical one. However, there is a dark, cold reality to this endless room. If space is infinite and expanding, the stuff inside it gets spread thinner and thinner. Think of it like a single teaspoon of sugar being stirred into a swimming pool. Then imagine that pool growing to the size of an ocean, then the size of a planet. Eventually, the sugar is so spread out that you could drink a gallon of water and never taste a single molecule. This is the heat death of the universe. In an infinite, expanding space, the galaxies eventually move so far apart that they can no longer see each other. The stars run out of fuel and blink out like dying candles. The black holes eventually evaporate through a process called Hawking radiation. What you're left with is an infinite expanse of absolute nothingness, a cold, dark void where nothing ever happens and nothing ever will. This is the ultimate destination of an infinite universe. It doesn't end with a bang or a wall. It ends with a long, lonely fade into silence. Does that make the edge of space more desirable? Would you rather live in a universe that goes on forever into a cold, dark nothingness, or a universe that is a small, cozy loop where you might eventually come back home? I find myself oscillating between these two fears. On one hand, the idea of a wall feels like a prison. It means we are limited. But on the other hand, the idea of forever feels like a desert. It's a room with no exit where the lights are slowly being turned off. But there's a catch. Some scientists argue that infinity is just a mathematical concept and that the physical world cannot be infinite. They argue that nature always has a cutoff. Just like there is a coldest possible temperature, absolute zero, and a fastest possible speed, the speed of light, there might be a largest possible distance. If that's true, then our math for a flat universe is missing something huge. It would mean that even if we don't see a curve, there is a stop sign somewhere that we haven't discovered yet. This leads us to a new information gap. If the universe is flat but not infinite, then it must have an edge. But a flat sheet with an edge is a very strange thing. What happens when you reach the literal corner of the universe? Do you just hit a wall of white light, or does physics simply stop existing? Imagine a 2D person living on a piece of paper. They can move left, right, forward, and back. If they reach the edge of the paper, they literally run out of existence. There is no more where for them to go. Could we reach a point in the cockpit of a spaceship where the forward button just stops working because there is no more forward left to travel into? As we move into the next part of our journey, we are going to move away from the giant scale of galaxies and look at the pixels of the void. But before we do, consider this. If there truly are infinite copies of you out there, living infinite variations of your life, then which one is the real you? Is the you reading this sentence more valid than the you 10 billion light years away who decided to skip this video? And if all versions are equally real, does that mean free will is just the universe exploring all possible outcomes at once? Is your life a single thread, or is it a tapestry woven from infinite choices happening simultaneously across infinite space? Up until now, we've been looking at space through a telescope, staring at the grand, sweeping curves of galaxies and the terrifying distances of the infinite. But to truly find where space stops, we might need to put down the telescope and pick up a microscope, the most powerful microscope ever imagined. When we think about the edge of space, we usually think of a wall far away in the distance. But what if the edge of space is actually right in front of your face? What if space isn't a continuous, smooth sheet of fabric, but is actually made of tiny pixels? In our daily lives, space feels perfectly smooth. When you move your hand through the air, it doesn't feel like you're jumping from one spot to another. It feels like a fluid, unbroken motion. But think about the screen you're watching right now. If you look at it from a few feet away, the image looks perfect. The colors blend together, the lines are sharp, and the motion is fluid. But if you take a magnifying glass and press it against the screen, the illusion shatters. You see that the beautiful image is actually made of millions of tiny square dots called pixels. If you try to look between the pixels, you can't. There is no in-between. You are either on one pixel or the next. Many physicists today believe that the universe works exactly the same way. This is the concept of quantized space. They suggest that if you zoom in far enough, past the atoms, past the protons, past the quarks, you eventually hit a limit. This limit is called the Planck length. It is a distance so unimaginably small that it's almost impossible to describe. To give you an idea of the scale, if you took a single atom and grew it to the size of the entire observable universe, the Planck length would be about the height of a single tree on Earth. At this scale, the very laws of physics start to melt. Our understanding of left and right, or up and down, loses all meaning. This is the quantum foam, a jittery, chaotic state where space and time are no longer stable. Virtual particles pop in and out of existence so rapidly that space itself looks like a boiling pot of water when viewed at this microscopic level. I remember a moment of personal insight when I was learning about this in college. I was sitting in a dark library, staring at a wooden table, and I realized that if space is pixelated, then movement is an illusion. When you walk across a room, you aren't sliding through a vacuum. You are essentially being deleted from one set of pixels and re-rendered on the next. We're like characters in a video game, oblivious to the grid we're moving on. But here is the unexpected story of the holographic noise experiment. A few years ago, a group of scientists at the Fermi Lab in Illinois built a device called a holometer. Their goal was to see if they could hear the pixels of space. They suspected that if space is made of tiny bits, there should be a fundamental jitter or noise as the universe tries to keep track of everything. It's like the slight graininess you see on a low-quality video. The holometer consisted of two perpendicular laser beams, each 40 meters long, that could measure distance changes smaller than the width of a proton. For over a year, the device listened to space itself, searching for the quantum static that would prove reality has a resolution limit. The scientists compared it to listening to the ocean while standing on a beach. If space is pixelated, there should be a background roar of quantum uncertainty. The results? They found nothing. Or rather, they found that if space is pixelated, the pixels are even smaller than they expected. But the very fact that we built a machine to listen to the grain of reality tells us that space might have a hard internal stop sign. We just haven't found it yet. If space is made of pixels, then space is not infinite in the way we think. It has a resolution. It has a bit rate. And this leads us to the most mind-blowing theory in modern science, the Holographic Principle. This theory grew out of a problem with black holes. Stephen Hawking and other physicists realized that when something falls into a black hole, the information it contains, everything about what it was made of and how it was shaped, seems to get smeared onto the surface of the black hole, rather than being lost inside. This led to a radical idea. Maybe the entire universe works this way. Think of a credit card. It is a flat, two-dimensional piece of plastic, but on that card is a small, shiny sticker with a hologram of a dove on it. When you tilt the card, the dove looks like it has depth. It looks like a 3D object sitting inside the card. But we know the dove isn't real in the sense of having volume. All the information needed to create that 3D image is stored on the flat 2D surface. The holographic principle suggests that our three-dimensional universe, everything you see, touch, and feel, is actually just a projection of information sitting on a 2D surface at the very edge of the cosmos. In this version of reality, the edge isn't a place you go to, it is the source code of everything you are. I struggle with this idea sometimes because it feels so fake. It makes me feel like I'm living in a movie instead of a world. But it actually solves the "where does space stop" question in a very clever way. If the universe is a hologram, then space stops at the screen. There is a boundary where all the data is kept, and everything inside that boundary is just a beautiful, complex light show. This creates a massive information gap. If we are a hologram, what is the light source that is projecting us, and what is the screen made of? In the world of string theory, some scientists talk about D-branes, which are like giant membranes that exist in higher dimensions. They suggest that our universe might be stuck to one of these membranes, like a piece of lint on a sweater. The edge of our space would be the surface of the membrane itself. But let's get even weirder. If space is just information, can it be full? There is a concept called the Bekenstein bound. It's a mathematical limit on how much information can be stuffed into a specific region of space. If you try to pack too much stuff, too many atoms, too much light, too much data into one spot, the space itself can't handle it. The pixels overflow. When this happens, the space collapses into a black hole. In a sense, a black hole is a place where space has stopped because it ran out of room to store the information. I once spent an afternoon at a museum looking at an ancient low-resolution tapestry. If you stood close to it, all you saw were rough threads and knots. It looked messy and incomplete, but as you backed away, a beautiful scene of a forest emerged. The threads of the universe are the Planck lengths, the pixels of space. From our distance, they create the beautiful, smooth scene of the stars, but at the edge, the tapestry must end. This brings us to a moment of vulnerability. If the universe is a digital-like projection, it means it is fragile. It means it relies on a set of rules that we didn't write and that we don't fully understand. We're like children playing in a sandbox, unaware that the sandbox has wooden walls and that someone could, in theory, just tip the sand out. But if we are a hologram being projected from a 2D screen, what happens to us if that surface gets damaged? Could cosmic rays or quantum fluctuations create dead pixels in reality? Regions where the laws of physics simply stop working?
Let's say we finally reach the edge. We have traveled trillions of years, past the last lonely galaxy, past the cosmic horizon of our vision, and we have finally hit the physical boundary of our reality. What do we see? Is it a literal wall made of some indestructible material?
Or is it a shimmering curtain of energy? One of the most popular theories in modern physics suggests that we wouldn't see a wall at all. Instead, we would see another universe. This is the multiverse theory, and it is the ultimate information gap. It suggests that our entire universe, everything from the Big Bang to the cup of coffee on your desk, is just one single bubble popping in a giant, eternal sea of other bubbles. Imagine you are standing in your kitchen, watching a large pot of water on a stove. As the water starts to boil, tiny bubbles of steam form at the bottom. They grow, they bounce off each other, and they rise to the surface. Each of those bubbles is a self-contained world. Within its own thin walls, a bubble is everything. But to you, standing outside the pot, they are just tiny parts of a much larger, chaotic process. In this scenario, space never truly stops. It just transitions. If you were to fly a spaceship through the crust of our bubble, you would enter the bulk, the vast, higher-dimensional space between universes. In the bulk, the rules of reality are completely different. We live in a world with 3 dimensions of space and 1 dimension of time. But in the bulk, there could be 11 dimensions. Time might move sideways or loop back on itself like a knot. Gravity might be a repulsive force that pushes things away instead of pulling them together. I want to share a moment of personal insight here. I remember the first time I heard about the fine-tuning problem. Scientists realized that if the strength of gravity were just a tiny fraction stronger, the universe would have collapsed back into a black hole seconds after it was born. If it were a tiny fraction weaker, stars would have never formed, and the universe would be a cold, thin gas. The electromagnetic force, the strong nuclear force, the weak nuclear force, all of them seem calibrated to within a hair's breadth of allowing complex matter to exist. It feels like someone carefully dialed in the settings of our world so that we could exist. For a long time, this felt like a miracle. But the multiverse turns that miracle into a math problem. If there are an infinite number of bubbles, then there are an infinite number of settings. Most bubbles are failures. They are universes where the math didn't work. Some lasted for half a second. Some have no light. We just happen to live in one of the lucky bubbles where the lottery numbers came up exactly right for life to begin. We are the survivors of a massive, cold, and indifferent process. It's a bit like a tree that drops a million seeds. Most of them land on concrete or get eaten by birds, but 1 or 2 land in the perfect soil and grow into a forest. We are that one seed. But let's look at an unexpected story of where these bubbles might come from. There's a theory called cosmological natural selection, proposed by the physicist Lee Smolin. He suggests that universes reproduce through black holes. Think about what happens inside a black hole. A star collapses down to a point of infinite density, a singularity. This looks a lot like the singularity that started our Big Bang. Smolin argues that every time a black hole forms, it pinches off from our space and gives birth to a new baby universe on the other side. The black hole becomes a cosmic birth canal. On our side, we see matter disappearing into an infinitely deep well. But on the other side, that compression rebounds into a new Big Bang, creating an entirely separate spacetime with its own galaxies, stars, and potentially its own confused scientists wondering where their universe came from. This would mean that our universe is a mother. Every black hole in our galaxy, and there are millions of them, might be a doorway to a brand new space. And here's the kicker. If those baby universes have slightly different physics than ours, then the universes that are best at making black holes will have the most children. Over trillions of billions of years, the multiverse would be evolved to create universes full of stars and gravity. It turns the entire cosmos into a living, breathing biological system. I find a strange, deep comfort in this idea. It suggests that space doesn't stop because it's constantly budding. It's a garden that keeps planting itself. Our universe isn't the end point of existence. It's a single flower in an infinite meadow. And from our seeds, new meadows will grow. But it also raises a terrifying question. What happens if two bubbles collide? If we're floating in a cosmic sea, then eventually our bubble is going to bump into another one. This wouldn't be like a car crash. It would be a catastrophe on a scale we can't imagine. The laws of physics from the other universe would bleed into ours. The sky might suddenly change color as different kinds of light pour in. Gravity might suddenly shift, or atoms might start to come apart. Stars could blink out of existence or suddenly ignite. The fundamental constants that hold matter together could change in the collision zone, creating a spreading wave of cosmic destruction. Some astronomers believe they have actually found evidence of this. They look at the cosmic microwave background, the baby photo of our universe, and they see a cold spot. It's a massive area of the sky that is much colder than it should be, spanning roughly the width of 140 full moons. While many think it's just a random fluke, some radical theorists believe this cold spot is a cosmic bruise. It is the spot where another universe slammed into ours billions of years ago, leaving a mark that we can still see today. Imagine you are a child playing with a soap bubble in the yard. If you bring another bubble close to it, they don't just bounce, they merge. For a split second, there's a vibrating, unstable wall between them before they become one large bubble. Could we be living in a universe that is currently merging with another one? And if we were, would we even know? Or would we just think the weird parts of our physics were normal? I remember sitting in a coffee shop once, watching the steam rise from my cup and thinking about the edge of the steam. It looks solid from a distance, but up close, it's just a blur of disappearing molecules. Our universe might be exactly like that steam. The edge of space might just be the point where our information becomes too thin to hold on to, and we evaporate into the bulk. This brings us to a new information gap. If the multiverse is real, what is it sitting in? If there's a sea of bubbles, is there a bottom to the sea? Does the multiverse itself have an edge? Or is reality just an infinite fractal, where every bubble contains black holes that make new bubbles which contain more black holes forever and ever? And this leads to the question that haunts cosmologists late at night. If new universes are constantly being born through black holes, and our universe contains billions of black holes, are we currently pregnant with billions of baby universes? Are we a mother who will never meet her children? And if universes can evolve through this cosmic natural selection, does that mean the multiverse itself is alive? A vast thinking organism made of universes the way our bodies are made of cells. If we're just one cell in an unimaginably large being, what happens when that being dies? Before there were stars, before there were galaxies, even before the first atoms had properly settled into their roles, there was a glow. It was a soft, uniform light spread across the entire universe like a warm, thick fog. It wasn't a spotlight or a fireworks show. It was quieter than that, yet more powerful than anything we've seen since. It was like the first rays of dawn seeping through a heavy curtain before you even open your eyes. This is the ghost of the beginning, and it is the closest thing to a physical wall we have ever found in our search for the edge of space. Scientists call this the Cosmic Microwave Background, or the CMB. It is the oldest light anyone can ever see, and it is a hard limit on our history. To understand why this light acts like a wall, we have to go back, way back, to the very first seconds of the universe. About 13.8 billion years ago, the universe began in a state of unfathomable heat and density. It was a searing soup of raw energy, light, and particles. For the first few 100,000 years, the universe was so hot that atoms couldn't even form.
Electrons and protons were flying around like a frenzied crowd in a mosh pit, constantly bumping into each other. Because there were so many free-roaming particles, light couldn't travel. Every time a photon, a particle of light, tried to move, it would immediately slam into an electron and bounce off in a different direction. Imagine you're at a concert and the room is packed wall to wall with people. You try to shine a flashlight to the other side of the room, but the beam keeps hitting someone's jacket, someone's head, or someone's hand. The light never makes it to the back wall. In those early days, the universe was opaque. It was like a thick, glowing cloud of smoke. If you had been there and somehow hadn't been instantly vaporized, you wouldn't have seen stars or planets. You would have just seen a blinding white fog in every direction. But then, at exactly 380,000 years after the Big Bang, something magical happened. The universe had been expanding, and as things expand, they cool down. Finally, the temperature dropped enough for the electrons to slow down and link up with protons. They formed the very first atoms of hydrogen. This moment is called recombination, and it is the most important unblocking in history. Suddenly, the mosh pit cleared out. The electrons were tucked away inside atoms, leaving vast amounts of empty space between them. For the first time ever, light was set free. It could finally fly in a straight line without hitting anything. The smoke cleared, and the universe became transparent. That light, that very first burst of freedom, has been traveling through the void ever since. For over 13 billion years, it has been flying through the darkness. But because the universe has been expanding the whole time, the light has been stretched. Its wavelength has grown longer and longer, moving from white-hot visible light into the infrared and finally into the microwave part of the spectrum. We first discovered this light almost by accident in 1964. Two astronomers, Arno Penzias and Robert Wilson, were working with a giant horn-shaped radio antenna in New Jersey. They were trying to listen to signals from space, but they kept hearing a persistent, annoying hiss. It was a low-level background noise that wouldn't go away no matter which way they pointed the antenna. They went through every possible explanation. They thought it was interference from New York City. They thought it was a malfunction in the electronics. At one point, they noticed a pair of pigeons had nested inside the horn, so they cleaned out the white dielectric material, pigeon droppings, and chased the birds away. But the hiss stayed. It was steady. It was everywhere. What they eventually realized, with the help of theorists at Princeton, was that they weren't hearing noise. They were hearing the birth of the universe. They were listening to the very first light that was set free 380,000 years after the Big Bang. That hiss is the CMB. It is the literal echo of creation. For discovering it, they won the Nobel Prize in 1978. I want to share a moment of personal vulnerability here. I remember standing outside on a cold night, looking up at the black gaps between the stars, and realizing that those gaps aren't empty. If we had microwave eyes, the entire sky would be glowing with the heat of the Big Bang. We are constantly bathed in the light of our own beginning. It's like living inside a house where the walls are made of old photographs of your ancestors. You can't see past them, but they remind you exactly where you came from. This leads to a massive information gap. The CMB is the ultimate curtain. Because the universe was opaque before that moment, we cannot use light to see anything that happened in the first 380,000 years. We can't see the Big Bang itself. We can't see the moment inflation started. We are blocked by a wall of fire. But does that mean there is nothing behind the wall? Think of it like a theater curtain. You can see the heavy velvet fabric and you can see it rippling as things move behind it, but you can't see the actors until the curtain pulls back. Scientists are now trying to look through the CMB by using things other than light. They are looking for gravitational waves, ripples in the fabric of space itself that were created in the very first trillionth of a second. If we can detect those waves, we might finally be able to see the stage before the light was turned on. There is an unexpected story about what the CMB tells us about the end of space.
When we look at the map of this ancient light, we see tiny microscopic fluctuations in temperature. Some spots are a billionth of a degree warmer than others. These spots are the seeds of galaxies. They show us where the dough was a little thicker. But here's where it gets weird. These temperature fluctuations have a pattern. They have a characteristic size, about 1 degree across the sky. This standard ruler allows us to measure the geometry of the entire universe. If the universe were closed and curved like a sphere, these spots would look bigger. If it were open and saddle-shaped, they'd look smaller. By measuring the size of these spots, we can calculate the curvature of the entire universe. The results are stunning. The universe appears to be perfectly flat within a margin of error so small it's almost suspicious. It's like looking at a sheet of glass that stretches for 1,000 miles without a single scratch. This has led to some scientists to suggest that our universe didn't start as a random explosion, but was stretched flat by a process called inflation, a moment in the first fraction of a second when space expanded faster than light, smoothing out any wrinkles. But if the universe was stretched flat, what was it before? Was it a tiny crumpled up ball of dimensions? And if it was stretched, did it develop any tears? I once saw a piece of ancient pottery that had been smashed and then glued back together. You could see the lines where the pieces met. Astronomers are looking for those same seam lines in the CMB. They are looking for cosmic strings, massive, thin defects in space that might have formed when the universe cooled down, like cracks forming in ice. If we found one, it would be like finding a zip in the fabric of reality. It would be a literal edge that we could study. So the CMB is a wall in time, but it might also be a map to the wall in space. It tells us that our universe had a clear beginning, but it also raises the most haunting question of all. What was happening before the light was set free? Was there another universe that died so ours could be born? In some theories of loop quantum gravity, the universe doesn't have a beginning. Instead, it has a big bounce. It suggests that space contracts down to a certain point and then bounces back out like a compressed spring. If that's true, then space has no stop. It just has a reset button. We might be living in the billionth version of a universe that has been expanding and contracting forever, each cycle leaving faint echoes in the next. This raises a curiosity loop that bridges to our final section. If the CMB is the oldest light we can see, and it shows us a universe that was once uniform and featureless, how did we get from that smooth, boring fog to the rich tapestry of galaxies, stars, and consciousness we see today? And more importantly, if there was a universe before ours that collapsed and bounced, could there be information from that previous universe hidden in the patterns of the CMB? Messages from a civilization that lived and died before our Big Bang. Are we reading the tombstone of a dead cosmos every time we study the background radiation?
So, where does space stop? The honest answer is that we do not know, and we might never know. If space is infinite, it never stops. If it is closed, it stops by coming back to the beginning. If it is a hologram, it stops at the boundary of information. If the multiverse is real, it stops by transitioning into another universe. Each answer opens a door to more questions, and every door we open reveals a hallway with 1,000 more doors. But I have realized that the where isn't as important as the why. We ask where space stops because we want to know our place in it. We want to know if there is a limit to how far we can go and how much we can be. We want to understand if we're significant or if we're just cosmic dust in an indifferent void. When I look up at the night sky now, I don't feel small anymore. I feel like a part of a grand, unfolding mystery. Whether the universe is a giant donut, a flat sheet, or a bubble in a sea of foam, it is our home. And the fact that we can even imagine the edge means that, in a way, our minds are already there. Think about that for a moment. Every other object in the universe just is. A rock doesn't contemplate its own existence. A star doesn't wonder what's beyond the galaxy. But we do. We are the only part of the universe that can look at itself and wonder about its own boundaries. We are the universe's way of asking, how big am I? Where do I end? What am I made of? In a very real sense, you are stardust that has organized itself in such a way that it can contemplate the stars. The atoms in your body were forged in the hearts of dying suns, scattered across the cosmos in supernova explosions, and eventually coalesced into you. You are not separate from space. You are a temporary pattern in the fabric of space itself, a wave in the cosmic ocean that has briefly become aware of the ocean. As you go about your life, try to hold on to that feeling. You are a walking, talking piece of the cosmos. You are made of the same fabric as the stars and the same energy as the vacuum. The edge of space isn't just out there. It is a part of the same story that produced you. But I want to share one final moment of vulnerability with you. Sometimes, late at night, I think about the question we started with. If we found a wall at the end of space, what would be on the other side? And I've realized that maybe the question itself reveals something profound about human nature. We always want there to be an other side. We can't help but imagine that beyond every boundary is another room, another world, another story. This impulse, this refusal to accept that anything is truly final, is what drives us to explore, to question, to push against every limit we encounter. Maybe the edge of space isn't a place at all. Maybe it's a question that will always be just slightly out of reach, pulling us forward into ever deeper understanding. Maybe the journey to find the edge is more important than the edge itself. But as we close this journey, I have to leave you with one final thought. If the universe really is infinite and everything that can happen does happen, then somewhere out there is a version of this story where the ending is completely different. In that universe, we have already found the edge. We have already seen what is on the other side. And if they could send a message back to us, what do you think they would say? Would they tell us to keep looking? Or would they tell us that the real journey was never about the edge at all? What if the edge of space isn't a physical place, but a level of understanding that we just haven't reached yet? What if, by the time we're capable of truly answering the question, where does space stop, we'll have evolved so far beyond our current form that the question itself will seem quaint, like asking where the sky ends when you're standing on the ground, not yet knowing that the sky is just atmosphere, and beyond it lies the infinite. The universe has given us consciousness, the ability to ask impossible questions. Maybe that's the point. Maybe we are the universe's way of exploring its own mystery. And in that sense, the edge of space is wherever our curiosity ends. But I have a feeling your curiosity doesn't end here. So here's my final question for you, the one that will determine whether you truly understood this journey. If space is made of fabric that can stretch, bend, and potentially tear, and if we've discovered that this fabric has been torn before in the form of black holes, what stops us from tearing it ourselves? Could future civilizations develop technology powerful enough to punch a hole in space-time, creating their own doorway to whatever lies beyond? And if they did, would that act of tearing open reality be an act of exploration or an act of destruction? Would we be opening a door, or would we be breaking the terrarium that keeps us alive? The universe is still writing its story, and you, yes, you, are part of that story. The question isn't where space stops. The question is how far will we go to find out?